kinda get it, just like the three directions, the three directions.
But I did, yeah, what I did, I
You got
split
your
it,
rate, right?
yeah, I split it up, I had J, K, so then I did it separate, like, 1, 2, 3. Then what you had one network equals connection, everything. So then you have, I had J hat, K hat. Okay, so then some of them had that.
Kyle, now's your chance to do a ninja jump over them.
Oh, sorry.
It's all good, go ahead.
I wanted to see the ninja jump. Alright, so we are missing Roberto, Enrique, nope, Roberto. And just Roberto. And Austin's around here somewhere. Alright, so let's start out with the usual. Are there any questions?
How do you do number 4 on exercise 9?
Is that, oh, that's the meteoroid?
No, that's the one with the work, and you have like I hat, J hat, K hat.
Oh.
And then you have to find final speed.
So ultimately it comes down to that the total force is, I gave you the conservative and non-conservative force. So you would add them together to get the total force. You know that the total force, based on the work energy theorem, the total force is equal to the change in kinetic energy.
Total work.
Yeah, total work, thank you. I wrote it correctly, I said it wrong. The total work is equal to the change in kinetic energy, which, despite what some students insist, is the final kinetic minus the initial kinetic. So 1/2 mv final squared minus 1/2 mv initial squared. The total work, since the force is constant, I believe. No, force is not constant. This will be the integral of the total force dot dx from some initial position to some final position. Since movement is only in the x direction, or I should say that, yeah, movement's only in the x direction. Actually, I don't think that's specified. We do know that the force is in the x direction, and so only the movement in the x direction matters. And so this is what you're trying to find here. I told you the initial velocity, and from that you should be able to find the initial speed. It's basically three-dimensional Pythagorean theorem. A squared plus b squared plus c squared equals d squared.
Oh wait, so you wanted the final speed in component form, but in
Yeah, I'm pretty sure it asks for the speed. So you don't need to get all fancy and try to find something else. Yeah, what's the object's speed? Did you wanna?
yeah. I left it in component form because you gave us the initial speed in component form, so I thought like you wanted the final answer.
No, I just went for that one number. I feel like I zipped through this and with a couple misspeaks. Is this sufficient? Any other questions about what I have said or other questions on this problem? Now, some people in the past actually find out what the initial speed is. You actually don't have to know the initial speed because they give it to you in component form. All you really need to know is initial speed squared. So you don't actually have to do that square root and then follow up with a squaring it later. But some people do just for completeness, or that's just the way their mind is working at that moment. And just don't tell Austin.
How would you do a Pythagorean theorem with the K hat?
With K? Alright, so if I have AI plus B Bj plus Ck, if that's some velocity, then the speed is the square root of a squared plus b squared plus c squared. You can actually derive it if you imagine that you're dealing with a cube. It's the distance between the corners. I'm probably drawing too many lines at this point. Because you draw the diagonal of just one side, that's just straight up Pythagorean theorem. And then, so now you've got, so you do a squared plus b squared equals c squared for that one. And then you now have this other right triangle here. That's a right angle. There. And you would just go through it again. All right, any other questions? All right, let's take a look at some rotational motion problems, or exploiting torque. So, has anybody actually figured out why I use the term Jitu Kabuka for torque? So I have some sort of beam right here. Let's make it 10 meters long. The mass is, let's make it 15 kilograms. It's being supported by two wires right here. And a small child right there. Let's say 10 kilogram small child. Level and uniform density. Uniform density of the beam, not the child. And let's have the child 1 meter from the end. And so let's see, the supports, we'll make that 2 meters, make that 3 meters. And what I want to know is tension in the wires. Make sure that it's still recording. Now, when we first were dealing with forces in chapter 4, 5, one of those, I think chapter 5, I'd have to give you one other piece of information, but now we have sophistication enough to be able to deal with it. So what's the first step?
Force dying.
Absolutely. So I have tension acting up on the left here, so I'll just call that FTL. Actually, I'm just gonna, it's tension, I'm just gonna label that L, just to eliminate some of the writing. There is definitely tension acting up here. I'm gonna call that cleverly R. All right, so there are my tensions. What are the other forces acting on the beam?
Weight,
Okay, where's the weight acting on the beam?
center of mass.
Which would be, since it's uniform density, in the middle. So this is weight of beam. And again, let's see, so if this is 0 meters here, this is at the 2 meter mark, 5 meter mark, 7 meter mark,
The weight of the child.
Yes. Technically, no, but in essence, yes. What's the force? Yes. But since the child, I guess I didn't state this either, the child's just standing there. So ultimately, it's a normal force acting down on the beam, which is equal to the weight of the child. And that is at 9 meters. Oh, Enrique.
What are those numbers, the 02579?
I identified when I made the problem where things are acting. So the left support is 2 meters from the left end. The right support is 3 meters from the right end. The child's 1 meter from the right end. So I just established 0 here and just work my way across. And the 5 meters comes from the fact that it's a uniform density. Therefore, the center of the beam should be where in essence, the weight is acting. For those of you who eventually get into civil engineering, you will not concentrate the weight at a single spot. You'll look at the weight across the entire thing, and then you can start getting into how much is the beam going to sag and things like that. That's for the future civil engineers. All right, any other questions up to here? All right, so there's the force diagram. What's next?
Coordinate axes.
Okay. Well, technically acceleration. What's the acceleration of the beam?
0.
Yes. It's just sitting there. It's not falling. So coordinate axes, what do you want to make positive? All right. What else? We'll get to the other parts of the coordinate system in just a second. So up positive, I'm going to call that J for right now, just because I lack imagination. All right, so after the coordinate axes, what's next?
Decomposition, but I don't think we have anything to do.
All right, then what?
The equations.
All right, so our equation of motion was based on F equals ma. We have our J equation right here. So what is my equation of motion?
L plus R minus WB sub B minus W sub C equals 0.
Okay. I gave you the two masses of the beam and the child. We can find the weights. It's easy enough to figure out what the weights are. But we have two unknowns here, but we have only one equation. So obviously, considering where we are in the book, what does our other equation have to be in order to be able to solve this?
Torque.
Yes. Now, if there's a natural hinge or a natural point of rotation, axis of rotation, it makes sense to put our axis there, but we have something that is not moving at all, so there's no natural place to put our axis. So we can put it anywhere we want. If there's no angular acceleration, it's not actually pivoting physically, we pick some place that's convenient. Where would you like to put our axis?
0.
I heard in the center first, so let's go for the center first. This is our axis of rotation. So now, since we're dealing with torque, we do need another coordinate here. We have up as being positive, but we need to decide about left, right, or in, out. I guess we could make them like that, but that's just making work for yourself. So left or right, positive? I'm gonna call that I, because again, lack of imagination. But once I've established that as my I and J direction, we do assume a right-handed coordinate system. So which way does K have to go if this is a right-handed coordinate system? Yep. So we will have a K equation. And we're just gonna go bit by bit as we work our way down it. So I have 4 forces here. Potentially 4 torques, so I have torque due to the left, plus torque due to the right, plus torque due to the weight of B, plus the torque due to the weight of C equals 0. All right, so let's start out on the left-hand side. So moment arm, remember that torque is R cross F. So in the case of the left force, with the center as our axis of rotation, what is the moment arm?
Isn't it the wire itself?
No. Now we're talking moment arm here. This R right here is a vector from the axis to where the force is applied.
Oh, so it's 2.
Not with our axis being in the center.
Oh, 3. Yeah.
Let's be formal about it right at this point. I mean, there are shortcuts that you can take, and some of you might be doing this in your mind, but let's be formal about it. 3 is the magnitude, but give me the full vector.
Is it 3 I hat? 3 I hat?
Closer?
-3?
Yeah. Because it's from the axis to the left-hand side, it's going to the left, and I said to the right was positive I. All right, so I have -3 I hat cross my force, which is L J hat, plus the right side is 2 I hat cross R J hat. The middle one, the weight of B is 0 dot weight of B. Let's do it this way. Negative weight of B J hat. Plus, and the one that is 4 I hat dot weight of C, negative weight of C J hat. Make that a little bit more obvious. I think that is only a little bit more obvious.
I have a question. Is there a reason why you did cross and then dot for the last 2?
Because I made a mistake. There we go. Thank you. All right, I cross J. Now we're sort of working our way across. We're doing each of these separately. So we have I cross J. No. I dot J is 0. I cross J is not.
Okay.
Yes. You put your hand in the direction of the first vector, and you want your fingers to bend towards the second vector, which is up, and your thumb points in the direction of the resultant, or the product. So this will be -3 K hat, plus, we have I cross J, which we've already established as K hat. So this becomes plus 2 R K hat, plus 0 cross WB, or K hat. And then I cross J, we just established as K, so this becomes negative 4 WC K hat is equal to 0. Why not K hat? I have K hat and everything right here. In order for this to work, then all the K hat terms have to equal, on the left have to equal the ones on the right. In essence, I'm just going to take this equation and it just boils down to, I'm going to rewrite that first equation. So I have L plus R, let's go ahead and do substitution, MBG minus MCG equals 0. And then the second equation, I have negative 3L plus 2R minus 4 MCG equals 0. This is my K hat equation, and this is my J hat equation. And that is a 2. I have 2 equations, 2 unknowns, definitely solvable. Just for the sake of ease, let's assume this takes place on a strange planet where G is equal to 10 meters per second squared. So this equation right here becomes L plus R equals 250. And down here, this would be negative 3L plus 2R is equal to 400. And at this point, it depends on how you like going about solving it. I'm just going to multiply the top one by 3. So this becomes 3L plus 3R is equal to 750. 5R is equal to 1150. R is equal to 230. Units? And so L must be 20 newtons, based on this equation right here. All right, that's the formality of it. I'm about to show some shortcuts. Questions up to here? All right, so the shortcuts. Instead of going through the formality of it, I know that the moment arm and the force are perpendicular to each other. So all I really have to do is look at the magnitudes, and then I figure out the direction, the plus or minus, by using my hand. So this is my pivot point right here, in the middle. So I've got a beam with pivot point in the middle. And there's a force over on the left-hand side, upwards. Which way is it going to cause this thing to rotate? Let's use the language. Better language. Yeah, clockwise from your point of view. What? Into the board.
Okay.
Yeah. It's going to rotate it around like that. The thumb points in the direction of the torque. So into the board. We said out of the board was positive, so into the board, so we got negative 3L. This one, no torque at all, plus 0. The right-hand side, got my pivot point here, because this force is acting up on this side over here. So plus 2R. And then we have this 100 Newton force here. Minus 100 equals 0. Sorry, 400. Multiply times 4, 100 times a 4. And we just jump straight to that equation. Questions to hear?
Isn't there, trying to think back to my past physics class, isn't there another way that you can tell if it's negative or positive?
Yeah, we just did like clockwise equals counterclockwise.
Ah, that works too.
Yeah.
Same way you could do forces up equal forces down.
Yeah, this one.
Now, one other thing we could have done, and I mentioned it before, if not in this class, in other classes, which definitely would help you. A great deal of physics, as you get more and more advanced, is trying to find a coordinate system that reduces the amount of math you have to do. Because remember, all of this was developed before computers, and so they wanted to reduce the amount of computation that's involved. The center was the first thing picked. The other thing I heard picked was over here. That works also. But if we could eliminate a torque from an unknown, that is going to reduce the amount of math we have to do. Which means here or here would probably have been the simplest choice in terms of math. If we pick the left one, if we pick this one as our coordinate system, or as our axis, I should say, the weight here is acting, causing torque into the board. So this equation now would become 3 times 150, or 450, negative. The right-hand side here, it's 5 meters away, and that's trying to rotate it counterclockwise or out of the board. So plus 5r. And then the weight right here is 7 meters away, and it's trying to rotate it counterclockwise from our point of view or into the board. So minus 700 is equal to 0. 5r is equal to 1150, which is exactly where we were over there. So picking an axis of rotation for something which does not have a natural axis, picking an axis of rotation which will eliminate an unknown generally makes life a little bit simpler. And we will definitely exploit that in the next example we do. Questions to hear? All right, let's go to the next more complicated one. The classic ladder and wall problem. Meter long ladder. We'll make mu's S equal to 0.5, and let's make this 37 degrees. This is a ladder. Mass of the ladder, 10 kilograms. Mass of a person, make 50 kilograms. The wall is frictionless, or if that bugs you, there are rollers on the end of the ladder which have been oiled recently, and so it is going to effortlessly move up and down the wall with no noticeable friction. The question is, how far up a ladder can a person go before it starts to slide? How far up can a person go without ladder sliding. And so we will assume that the person is some distance x up. All right, so first step,
Force diagram.
yes. Assume ladder is uniform density. Uniform density, or at least close enough so that its weight is acting smack dab in the middle. Weight of ladder. What else?
The weight of the person.
Similar to what before, technically, normal force, but it's gonna be equal to the weight because the person's just standing there. We assume that the person is moving so slowly that there's no noticeable acceleration for the person. The person is just, if you've ever seen the TED Talk, I think it was a TED Talk, the League of Extraordinary Dancers, the guy who walks in slow motion. That's the kind of thing we're talking about here. So he is somewhere, now where I draw it is part of an artistic expression here. It's someplace X, I'm just gonna put it here. So we have the Y from the person, which should be equal to the weight of the person in our case. It is acting down. Why is it not acting at an angle?
He's not standing at an angle
Why?
because the ladder has straight.
Yeah, you stand on rungs, it's not a ramp. That's some distance X. X. That's 5 meters. All right. 2 down, 3 to go.
Would there be friction on the wall?
No, this was to indicate that there's no friction on the wall.
Okay.
Then
On the ground.
the friction going that way.
Yes, it is indeed going that way, because if it slipped, the bottom is gonna be moving off to the right, so the friction has to be acting off to the left.